So the structure pop quiz 7. Can ask your doubts. Question 1. A. Any doubt? A, B, C. C1, should the height be negative? And C2. A ball is dropped from a rest. Assume that the air is negligible. What is the final speed? No, not really height, because this object is dropped. So height you should not take as negative. Why you will not take as negative? Because only one motion is there. It's a downward motion. So when it's a downward motion, acceleration is acting downward. So it will be 9.8. That is also the height. The distance is also downward. So all are in the same direction you are measuring. So don't take height as negative. Take it as positive. And use a formula like GP is equals to KE, like loss in potential equals to gain in kinetic, and work out the kinetic energy. Work out the speed. If you use the equation of the motion, you will get the same result. Like here, initial velocity is zero because it's a one. Look, when there is a one dimension motion, like a object is moving downward. So in that case, I don't have to take display because I'm taking all the downward direction as positive. So the displacement will be 4.5 and acceleration is also downward 9.8 meter per second square. And I need the speed at which it hits. So if I use the equation of motion 2as equal v square minus u square, so I will substitute the positive values as I'm taking all the downward direction as positive. Any other doubt? C2, part C2. Okay. The ball has a mass of 15 grams and a radius of 1.2 centimeter. The numerical value of the constant C in the equation for B is equals to 3.2 exponent minus 4 negative 4 when measured using the SI system of units. Show quantitatively whether the assumption made is justified. What is the assumption made in one? The assumption made in the one is like there is no air resistance or it is not losing any energy. So what we will do, the spherical ball of a radius r experience a resistive force as it moves through the air with a velocity v. And the resistive force is given by this expression. So what we can do, we can use this expression to work out the resistive force. So how to work out the resistive force? Resistive force F is CRV. Why are we working out F? Why not work out V instead? Yes, you can work out both ways. You can work out the V, like what we are doing. We'll work out the resistive force and we'll compare with the weight of a sphere. If it is like very small, what I'm doing right now, look, as the sphere is falling, the weight of a sphere is downward and the resistive force is upward. What we will do, if the resistive force is very small compared to that of a weight, we can neglect that. And when we neglect, so we ignore the air resistance. So it's actually this question, you have to compare the weight and the resistive force and just compare the proportion, like what is the value. So the resistive force according to the question is equals to CRV. The value of the C is 3.2 into 10 to the power minus 4. The mass, it is 15 gram, but it should be in kilograms. So we have to divide by 1000. But and what about the radius? It's sorry, radius is there 1.2. We divide by 100. So 0.12, 0.012. The speed at which it was moving, we calculated what was the speed in the last part? 9.4. So we put 9.4. If this object is moving at a speed of 9.4, what is the resistive force? We'll work out. So 3.2 exponent minus 4 into 0.012 into 9.4. What's the answer for the resistive force? So it is 3.6 into 10 to the power minus 5. That's a resistive force. The force which is opposing the motion is this. The downward force is a weight, which is mass into gravity. Mass is given in gram. We have to convert into kilograms. So divided by 1000. So it will be 0.015 times the gravity 9.8. So what is the weight here? What is the weight? So 0.1, approximately 0.15 if I take 10. Approximately 0.15. So if you compare the two forces, 0.147 or 0.15, if you compare these two forces, weight, the downward force is 0.15 Newton, where the upward force, the drag force is 3.6 into 10 to the power minus 5 Newton. So what is the ratio between them? If I divide, if I divide this, if I want to take a simplest ratio, 0.15 and 3.6 into 10 to the power minus 5. So how many times the weight is? So it's like 4,000 times, 4,087 times. So it's too big. So it means that this can be justified, like the resistive force is negligible. So we can assume that there is no air resistance acting. Is it clear? So when it is hitting the ground at a speed of 9.4, the resistive force is a very small value, so which can be ignored. So it is justified. Question 2, any doubt? 2B and C, okay. Okay, Mad, I will explain the last part again. See what we did. The question is show quantitative whether the assumption made in one is justified. What was the assumption made in one? The assumption which was made in a one, that the air resistance is negligible. Like you don't have any air resistance, or a drag force is negligible. So what we did, we calculated the weight, which is the mass times the gravity, and we calculated the resistive force, which is given in the first part of the formula, that resistive force is CRV. So, so the resistive force is CRV. The value of the C is given to us, which was 3.2 into 10 to the power. The value of the C, 3.2 into 10 to the power minus 4 was given. The radius was 0.12. It was 12 centimeters, so 0.12. And the speed it was moving, like this part, it was 9.4. So when we calculated, we got 3.6 into 10 to the power minus 6 Newton. That's a resistive force. But when we calculate the weight, which is mass 0.015 times 9.8, so approximately equals to 0.15 Newton. So when I compare the downward force with the resistive force, so the resistive force is negligible. I can ignore that because if I compare the ratio, it is like 4,800 times compared to this one. So I can ignore the resistive force as the weight is much greater than the resistive force. So it is justified that we ignore the air resistance with this speed or a distance from which it is dropped. Is it clear? The next is rod AB is hinged to a wall at A. The rod is horizontally by a mean of a cord BD, as you can see, attached to the rod at NB and the wall at D, as shown in the figure. The rod has a weight W at the center of a gravity of a rod at C. The rod is held equilibrium by a force T of the cord and the force F produced by the hinge. Part B, the line of action of a weight of a rod passes through the cord at point P. Explain why for the rod to be in equilibrium, force F produced at the hinge must also pass through point P. Like these two forces, when we draw this line and we do this line, why the two forces must pass through the same point, and this is in equilibrium, balance. So when object is in equilibrium, the resultant force should be zero. When like object is in equilibrium, the resulting turning effect should also be zero and the resultant moment should also be zero. So, or when we make a force triangle, like what are the forces which are acting? The force F is acting here. Force T, the tension is there, and a force W. So when I complete a triangle, I should get a resultant force to be zero. So first we do F, then I do T, and when I will draw the W, so I will reach the same starting point. So whenever object is in equilibrium, number one, the force triangle, the triangle of the force or the resultant force should be zero. So the first condition, when both F and T are passing through point P, the force triangle or the triangle which is formed, the resultant force, that will be zero. That is one thing. The second thing, is it clear the first point? When object is in equilibrium, when we sum all the forces, like add all the forces, we should return back to the same point. So one of the reason why the force F should pass through point P and the force T also pass through point T. So when we get the result of these forces, the force triangle should be complete. It will be a triangle and the resultant force will be zero. Yeah, resultant force will be zero when the starting point and the final points are same. That is one thing. Another thing is due to the turning effect, the moments. So the resultant force, the moment or the turning effect, which is caused by the T, the turning effect which is caused by the T and the turning effect which is caused by W is around what point? It is like P, this point P is the intersection of the intersection point of turning point for this, where the two forces meet. Yeah, the pivot, original pivot is A, that's right. But when we work out like about the turning effect or the at certain point, so F is acting on this point, W is acting downward and T is acting here. So the question is why F should passes through P, T should also pass through P, and the W is also passing through P. So what is the main reason? The first reason, as I mentioned, that there should, when object is in equilibrium, the resultant force should be zero. There should be no resultant force. And to have a no resultant force, all the forces should act at a one point. That's why the force F, the force T, and the force W should intersect at point P. Is it clear? For an object to be in equilibrium, all the forces must act at a single point. So when we get the result will be zero. Is it clear the reason? So how do we put the answer in this question in words? So how you'll put the answer in words? First thing you'll mention, this rod is in equilibrium. When object is in equilibrium, what are the conditions for object to be in equilibrium? There should be no resultant force and there should be no resultant turning effect. So how we'll have a no resultant force or the result of the forces is zero. So the all forces should meet us at a single point. If the forces are not meeting a single point, the result cannot be zero. Like if I say this is an object, here's a force F is there and another force F is here. So what will happen? This object will not be in equilibrium, will not be in balance. It will rotate. So to be in equilibrium, all the forces should meet at a single point or start from a single point. So if I mark this point P, the force F is there, the force T is there, and the force W is there. So they meet at single point. This given evidence that this should be in equilibrium. So to write an answer, object is in equilibrium. There should be no resulting turning effect or the no resultant moment. So all the force should start from a single point. That's why F, T, and W will meet at point P. Is it clear? The next is you need an equation. Force F and T make an angle alpha and beta respectively with a rod AC, with a rod, and AC is 2 by 3 of AB as shown in the figure. Write down equation in terms of a W, F, W, T, alpha and B to represent resolution of the forces horizontally, resolution of the force vertically, and moment about A. So if we resolve the forces horizontally, if you resolve the forces horizontally, so this is with an angle, so this will be equals to F cos alpha, and this is opposite to the angle, that will be equals to F sin alpha. For T, this is with an angle, so this will be equals to T cosine beta, and this is opposite to the angle, so this will be equals to T sin beta, and the weight is acting downward. Now we want to resolve, like we want to compare. So as you can see, F cos alpha is acting towards the right hand side horizontally because we want to resolve horizontally. So F cosine alpha is acting right and T cos beta is acting left. So because it is in equilibrium, so I can say that F cos alpha minus T cos beta will be equals to zero. The horizontally no force is there, or I can also say F cos alpha is equals to T cos beta. Is it clear? And then in a vertical plane, T sine beta is acting upward, F sine beta is acting upward, and weight is acting downward. Why not two force add? Why two forces are not added? Because they are acting in opposite direction. T cos beta is acting towards right, and F cos alpha is acting to sorry T F cos alpha is acting towards right, and T cos beta is acting towards left. They are in opposite directions, so I should subtract them to work out the result. Same way, the weight is acting downward and T sine beta and F sine alpha are acting upward. So I can say weight minus T sine beta minus F sine alpha will be 0. Or if I move them other side, I can say weight will be equals to T sine beta plus F sine alpha. Is it clear? This one? The vertical plane. This was the equation for the vertical. This is the equation for the horizontal. Next is the moment about A. So A is a pivot here, taking a moment about A. So if I take the moment about A, you can see this force F will not cause any turning effect. Why it does not cause any turning effect? Because it is acting on the pivot. When force act on the pivot, like here is the point of rotation for us. So when force act on the pivot, it does not cause any turning effect. So there is no turning effect of this one. So the two forces which will cause a turning effect, the two forces which will cause a turning effect, one is the weight, which will cause a clockwise turning effect. Another one is a tension, the component of the tension, which is T sine beta. So this will cause an anti-clockwise turning effect. So one is causing a clockwise, another one is causing an anti-clockwise. And because it is in, why we ignore this? Because it is acting on the pivot. And what about the distances of these forces? It's given in the question. Then the length AC is 3 by 2 of AB. So length AC, this length is 3 by 2 of AB. So when we calculate the turning effect, the clockwise, so it will be weight multiplied by 3 by 2 of AB, the distance from the pivot, this distance, and the force T sine alpha, T sine beta, multiplied by distance from the pivot. So distance from the pivot is AB. So we put AB. 2 by 3 of AB. Okay. Sorry. Yeah, by mistake, I put 3 by 2, 2 by 3. So it is 2 by 3 of AB. And it is obvious, like it cannot be more than that. It is smaller, so it is 2 by 3. AB will cancel with AB. So it is 2W is equals to 3T sine beta. So that is a relation between these two forces. Is it clear, this one? Next is question 3. Any doubt in question 3? 3A, B, C. 3A, B, C, all doubts, okay. 3A, state with a reason whether the spring undergo elastic change. So how you'll identify the it undergo elastic or a plastic? Look, the deformation is a linear deformation, like linearly change. It's a not a non-linear change. It's not a curve. So this give an idea that it is an elastic deformation. And we don't find, like example, it will become how to identify elastic or a plastic. If it was having a loop, like we were having a loop like this, or we were having a loop like this, then we can predict. But in the question, when we apply the force on the spring and then we decrease the force, so there is no extension Figure 5.1 shows the variation of a force as a spring force is increased and then decrease to zero. So when we increase and then we decrease to zero, we return back to the origin. If it was a plastic deformation, then it will not return to the origin. Because plastic deformation, the object deformed, so there is no force, it will have some extension. But in elastic deformation, when the force is removed, the extension is zero. So as you can see, when the force is removed, the extension is zero. So this is an elastic deformation, not a plastic deformation. State with a reason whether the spring undergo elastic change that we did. In part B, the extension of a spring increased from x1 to x2. Show that the work done of extending the spring is given by this expression. So how we will know, like example, how much work is done on the spring, the work done on the spring when we move from x1 to x2, area of this part. Area of this part will give us how much work is done on the spring. To stretch from x1 to x2. So what we can do, if I take the area of this triangle first, which will be half force into extension, then I will take the area of the second triangle, which is also half force 2 into extension 2. And when I take the difference, so it will be half F2 x2 minus half F1 x1 when I take a difference. So it will be half F2 x2 minus F1 x1. And because it is the same spring, so we have the formula F is equals to Kx. So F is equals to Kx. In place of F, I can replace Kx. So if force is F2, extension will be x2. If force is x1, extension will be x1. So in place of F and F1 and F2, I can replace. So it will be 1 by 2. It will be K x2 into x2 minus half K x1 into x1. When I simplify, it will be half K x2 square minus half K x1 square. When I take like 1 by 2, K is a common, so it will be x2 square minus x1 square. Why square? Because if you see, x2 is multiplied with x2. So when x2 multiplied with x2, it will become x2 square. When x1 multiplied with x1, it will become x1 square. And the energy stored in the spring, energy stored in the spring is given by a formula half force into extension, or it is also given by a formula half kx square. Both formulas are used. So half kx square or half f is to x. Because f is equals to kx, so in place of f, we can substitute kx. So when we substitute kx, it will become half kx square. So area of this one, I can say it will be equals to half. Area of this triangle, it will be equals to half kx1 square. Area of the second triangle, I can say half k into x2 square. And then we just take a difference of half k x2 square minus half k x1 square. So when you subtract, so it will be half k common, x2 square minus x1 square. That will give us how much energy stored or how much work is done to move the spring from extension x1 to extension x2. Is it clear? So remember this formula, the energy stored in the spring. Then in part C, the trolley has a mass of 850 grams, which is held between the two fixed points. When the trolley is in equilibrium, the spring of each spring extended by 4.5. The extension of a spring is 4.5. The spring constant is 16 Newton per centimeter. The trolley is moved at a distance of 1.5. So if a trolley move a distance of 1.5, both springs have an extension of 4.5 and 4.5 in the when it is equilibrium. But when the trolley is moved at a distance of 1.5, so one spring will be compressed, so it will have an extension of 3, and the other spring will be stretched to 6 centimeter. The extension will be 6 because one will increase as it move 1.5 centimeter. So one will have an increase of 1.5, another one will have a decrease of 1.5 compressed. So this will be 3 and this will be 6. The trolley is moved and this causes extension of one spring to increase and the other to decrease. The trolley is then released. We release the trolley. The trolley accelerates and reach a maximum speed. Assume that the spring obeys the Hooke's law. Use the expression in B to calculate the maximum speed. So how much work is, as you can see here, expression in B. Expression in B, this is a work done on the springs, the system. Like not only one spring, this is a total work done on the springs, the spring system. So what is the extension of the one and the extension of the other by using this same formula? So one is extended, like one is increased by 15 centimeter, another one is decreased by 15 centimeter. So you just have to substitute the values for the extension, the value for x1 and x2, or without using this formula, you can also use your understanding that the work done is equals to half k x2 square minus x1 square. That is the total work which is done is given by this formula. And this work which is done will be converted into the kinetic energy. Yeah, work done will be equals to Ke. So how we know the total change, the total kinetic energy? Just substitute, like example, one of the spring origin, but remember one thing, the springs were having, like originally the springs were 4 centimeter extension for each spring, like this is 4 centimeter extension. The other was also having 4 centimeter extension. One of the spring extended, increased by 1 point. So now the new extension is 6 centimeter. Okay. And the other spring will be compressed. So the new extension will be 3 centimeter. So what we will do, we'll calculate the total work done, like total, because the energy stored in the trolley will be energy of the one spring plus the energy of another spring. And then it is released because one spring is compressed, another one is being stretched. So how much energy gained by the spring? Which do we take x2? It's up to you. Anyone you can take x1, the other one will be. This is a formula for energy stored in the spring. The extension of a spring is increased from x1 to x2. This is for one spring. The work done in extending the spring is given. So this is a work done on one spring. You will calculate the work done on the second spring and then total. So when you calculate the work done on the first spring, the work done will be half K. The new extension should be greater than the first one. So example, originally it was 0.06. Originally example, it was 0.06 square minus, originally it was 0.04 or 4 centimeter. and now it is 6 centimeters, so it is greater minus smaller. So it will be 0.045 because it is given in centimeter, we have to convert into meter. And the spring constant is also given to us. That is one of the spring which is being stretched. What about the spring which is being compressed? How much work is done on that spring? So it will be half K. The new value is what? 0.03, the 3 centimeter, minus the original extension was 0.45. Why I'm doing separately? Because this is a work done. This equation is a work done on each spring. So one of the spring is being stretched, another spring is being compressed. So I want to know how much energy is there in this system. When one spring is compressed, another one is stretched. So we use the same formula to how much it is extended and how much it is compressed. And the total, when we work out the total of this energy, because one spring is compressed, another one is being stretched. So after working out the energy of one spring and the second spring, we'll add the two energies. That will give us the total work done, which is W1 plus W2. And then the total work done will be equals to kinetic energy, that is equals to half mv square. Is it clear? Any doubt in this? Any question or doubt? Then we have the last question, question 4. Any doubt? You have to use a state conservation of momentum and calculate the total momentum before and after to work out the speed at which the aluminum sphere will move. Yes, you can also do the same thing. First, you will, there's also another way to do the same question. First, you will find F is equals to Kx and F is equals to Kx, okay? So you will work out the force because one of the spring is being stretched, another one is being compressed. You will work out the resultant force. After working out the resultant force, you will work out the work done. Work done is a force into distance. So resultant force into the distance move, that will give us the work done. And that work done will be equals to Ke. That's another way of doing the same question. D is the distance it moved. It's given here, it moved 1.5 centimeter. So both ways are acceptable. But in the question, specifically they mentioned use the expression in B. That's why you have to use that. Other method, why it will not score any mark? Because in the question, it is mentioned that use the expression in B. So this was a pop quiz. Next session, like tomorrow, I will explain the topic. Any question or doubt related to the class today?